The next talk is Jeffrey Vetter is going to talk to us about making SDRs more portable in the area of heterogeneous SoCs.
Good afternoon, everyone. I hope you had a chance to go out and grab some lunch. It's an interesting experience here. My colleague Sayong Lee is with me, and he's going to help me give a part of the talk. So you've already heard several of these things this morning where people are porting SDR to different heterogeneous architectures. And I would argue that's not just an SDR phenomenon. We're going to see that everywhere. At DOE, for example, all of our next supercomputers are going to be GPU based. And so we have lots of users struggling with how to port to these architectures. So we're part of the DSSoC program, and we're investigating the performance portability SDR. We've done a lot of profiling and trying to understand target architectures, and this really isn't different from what we do with our DOE applications. It's different software, of course, but we sit down, we don't know astrophysics, we don't know materials design. We sit down with those people and try to learn how to make their applications perform well on these architectures, and so that's what we're doing here. We're trying to use open programming models to do this. One of the things that's really important is future-proofing your application, so you don't have to worry about new architectures needing to recode your application because of that. And then finally, intelligent runtime systems. We've heard a lot about earlier. We think that's going to play an increasingly important role in addition to code generation and the performance of the applications. And the goal that we're looking at is being able to take, untouched, the same application and run it on a Qualcomm Snapdragon and run it on the largest supercomputer in the world. And just see if we can meet that goal. Now, it may not happen, but that's the challenge we're aiming for. So just a short note about specialization. So I love this chart by Ray Kurzweil that talks about the growth of computing since 1900, and it really shows you where we are today. We're nearing the end there, where we've had some outstanding gains from CMOS scaling and other things. Now we're really getting into this transition period, and I label it the sixth wave. I think there's a lot of things that are going to happen, and we're already seeing a lot of this. The first one is people are really specializing their applications and optimizing their code for the architectures we have. The other one that I'm not going to talk about is emerging technologies. Have you seen all the excitement about quantum computing and neuromorphic computing and all these other things? That's what people are looking for, really the next computational paradigm. Today, I'm going to really focus on architectural specialization. I think this is where we'll be for perhaps 10 years or more, where we take the CMOS, which is an incredible technology, and just specialize it for workloads. And so that's the specialization part. And it's really important that you get the specialization right. Now, a consequence of that is that the architectures start to yield very complex programming models. And this schematic I use for talking about high-performance computing in the sense that, even if you are in astrophysics or materials design or climate modeling, your application these days has to be made up of this stack where you have maybe MPI, some threading model on the SMP, and then if you're using an accelerator, OpenACC, CUDA, OpenCL, something like that. And it really varies across platforms. CUDA is not available everywhere. Of course, it's proprietary. Other things like OpenCL may or may not be available. And so when you look at it in that context, really, and this is generally for the DSSoC program, is first, how do you design that architecture? I show up on your doorstep and say, I have 10 billion transistors. They're yours. What do you want on your chip? How do you analyze your workload? And so part of our project focuses on looking at SDR to try to understand what those features would be. The second one is programmability. Is it really possible to design an application with one language and programming model that will run across all these architectures and you get reasonable performance out of them? That's, a question, but it's going to impact all these teams writing applications and software. They only have so much time to spend on science and porting software. And so this was the DARPA program, and it has, 3 different areas. Some of them I've already mentioned, and I'll talk more about in a moment. But the important part here is you really do assume that you're going to have, SoCs, and they're going to be very diverse. I'm talking way more than an ARM CPU and an ARM GPU. They may have inference engines, they may have FPGAs and other things on them, and you've already heard about some of the complexity dealing with those when you just have one. And so the overall structure of our project really started out like this. We were looking at applications. We're using a ontology framework to try to capture the differences and the properties of things in SDR. Then the programming system is what Se-Young's going to talk about. This is really static analysis and code generation. So if you're going to run, your SDR module on an FPGA, you just heard a great talk about what all goes into that, right? Is there any way we can simplify that? And then next, you've got the runtime system. And there's a big question there. Will Linux evolve to handle all these heterogeneous processors and memories that are coming its way? Or will that be handed off to another runtime system? And we've developed a prototype runtime system that I'll tell you a little bit about that's trying to explore that space. And then finally is the hardware. And several of the teams in DSSOC are actually building hardware. We're not, but we're reaching out and making use of some of the more complex systems out there. And this is just a kind of a timeline of how we see this manifesting itself over time. I'll skip that due to time. So let's just talk a little bit about the range of hardware that we are thinking about. So as I mentioned earlier, we run on Summit right now. And this schematic you see, it's 200 petaflop system at Oak Ridge. It's got 27,000 voltage GPUs in it. And they're all configured in this node schematic you see here, where you've got 6 GPUs and 2 Power 9s. Getting all those programming models that I was talking about to work properly and efficiently on that is very complex. And then you add the fact that you've got thousands of other nodes like this that are communicating at the same time and potentially doing I/O, and it's very dynamic, a very dynamic system. We just heard a nice talk about FPGAs and being able to use them for signal processing. We're looking at those. And then more recently, we've been looking at NVIDIA's Jetson. And so this is, again, it's an SoC, but it's very much an aggressive design. It has ARM cores, it has a voltage GPUs, smaller than what you get on a V100. It's got a deep learning accelerator and some other things like vision processors and vision processing accelerators. That's, when you get right down to it, that's what we think the future is going to look like. We're going to have, thousands of SKUs of different types of processors, and you're just going to buy the one that fits your niche. And then, of course, there's Snapdragon. This is the one that we're focusing on this year, and it is not as well known, but more popular than the Xavier that I just mentioned, because they're cell phone chips, right? They're very complex. They've got ARM big and little cores. They have vector accelerators. They have a tensor accelerator, like a training engine, and then different codecs and things like that, in addition to all the I/O for connectivity to 5G and so on. So it's a very growing space, and it seems to be accelerating. So just a word about some of the application studies that we're doing, and we have some tools that we'll make available if you're interested in looking at those. So when we put together apps, we're not experts in SDR. We're learning a lot, and so we wanted to go out and get some workflows that would allow us to understand how to profile and how to analyze these. We started with the Wi-Fi one, and it's in part because we really understand how to measure the performance of that on a application level. You know, if you do a file transfer and you're running it across this flow, you can get some real feedback as to error rates as well as throughput. And so that's something that we've been studying. We've also built tools, and these tools that really focus on the ontologies and the performance analysis that I mentioned earlier. The first few were really looking at all the flows in the system, and the later ones are more for profiling that. So we built some frameworks that let you put these flows up, run them for say 30 seconds, and then do a profile of where you're spending your time in the flows. This is an example of where some of the time is going. And you know, it's pretty much a normal profile. One of the questions is, are we getting representative flow graphs, and is 30 seconds really sufficient? The cooler looking analysis is this block proximity analysis. And so what we did was look at CGRAN and some of the other repos we had access to. And what you see in this graph over here is really a networking diagram where the nodes represent basically how many times they're used, and the weights on the edges represent connections between those and workflows. So, and this is useful, for example, if you're trying to combine operators that you can put on an SoC that's coming down the line, or maybe optimize by creating a new module, for example. And that was, let me see if I got the, so all of these tools are available down here on GitHub. We'd love feedback on them. So next, working our way down, the programming systems is where we've been spending a lot of time recently, as well as the runtime system. So I'm going to let Seong tell you about our programming strategy.
Yeah, I'll talk about the programming system that we use.
You're on.
Yeah, I'll talk about the programming system that we use to port the GNU Radio blocks to the heterogeneous devices. This gives the overview of the system. As you can see, we use two compilers, the base one. One is the OpenArc, and the other the LLVM. OpenArc is the homegrown compiler developed by us. And we use the multiple programming model like the OpenMP, OpenACC, Iris, and HIP, CUDA, OpenCL. So by looking at this figure, it may not be easy to understand what's going on in the programming system. So let's look at the concrete example. So this shows how we port your GNU Radio blocks to the heterogeneous device using our framework. So basically what we assume is that user can write a program using the high-level programming model like OpenMP, OpenACC. In this example, suppose that user write a GNU Radio block using OpenACC. Then our compiler performed the source translation and generated output program depending on the target architecture. That means that if you want to run your own GNU Radio block on the NVIDIA GPU, then our compiler generates the output CUDA task, and it will run on the NVIDIA GPU. And if you want to run the blocks on the, for example, ARM or other Xeon file like a CPU, then our compiler will automatically generate the output OpenMP program and running on the Dojo architecture. Likewise, depending on the target architecture, our compiler automatically generates the output kernels. And one good thing about our framework is that no matter how different type of output programming models are used, we use a common runtime called Iris. That's another runtime system that we developed by ourselves. So one benefit of having common runtime interface is that you can write the application where one task is running on the GPU using CUDA, and another task running on the CPU using OpenMP, and yet another task running on the FPGA using OpenCL, something like that. So that kind of true intermixing of the multiple different output programming models is possible by using our framework. And we also support several other new ones, like HIP is another GPU programming model developed by the AMD. We also support like another new one called the SQL, but I will not talk detail about these new programming models. And for example, if you want to port your GNU Radio blocks on the JBL like SoC, then we can use the CUDA for the JBL GPU and OpenMP for the JBL CPU. And this shows the code structure of the OpenACC block. As you know, the original GR blocks are written as a C++ class, and we follow the same structure. That means that if you want to write your own OpenACC GR block, then you have to write this type of class. But one common requirement is that every OpenACC block should inherit the parent class called the GRACC base block. What it does is that it initializes the data structure used by the OpenAC runtime, and it also assigns the unique logical thread ID to each block instance. Actually, the reason why we need that kind of the parent class is because of the multi-threading issue. As you know, as you learned in the morning session, original GNU Radio framework provides multi-threading. That means that multiple GR blocks can execute by the multiple different threads. But the problem is that our OpenAC runtime also supports multi-threading. But the problem is that original GNU Radio block, the framework uses the C++, the Boost threading library-based multi-threading, while OpenAC runtime uses the OpenMP-based multi-threading. So two systems does not know each other. So to handle the multi-thread safety issue by integrating two different programming, so what we did is that we introduced the concept of the logical thread. By using the logical thread ID, the OpenAC runtime knows that what kind of the thread local data structure should be used. So it's a low-level detail about how to enforce the thread safety when we integrate the multiple systems. So I'll not explain all the detail. But anyway, in this OpenACC block, we provide two implementation. One is the reference CPU implementation, which is just exactly the same as the original GNU Radio block. And OpenAC implementation, that's the OpenAC version of the reference CPU version. If you write the basic OpenACC implementation, it will perform the three types of tasks. First, at the beginning of the invocation, it should copy the data from the host memory to device memory and launch the device kernel. And at the end of the execution, we have to copy the result back to the host memory. This shows the example translation of the OpenAC block. As you can see in the left, it shows the simple OpenAC block for the GR log module. What we did here is that in addition, on top of the existing CPU implementation, we just add the one line of the OpenAC directive. Then our compiler automatically generates the output host program and the kernel program, depending on the target architecture. And this shows the example workflow where we used our own OpenAC GR block. So as you can see here, top workflow use our GR OpenAC block. On the other hand, bottom workflow use the original reference GR blocks. So the only difference is that both workflows do the same thing, but one uses the OpenAC block, the other uses the reference CPU implementation. And this shows the basic management scheme for the OpenAC enabled GR workflow. So because the what OpenAC does is that it offloads the computation to the device, which can be a CPU, GPU, FPGA, whatever. In this case, what happens is that when OpenAC block 1 is invoked, first it should copy data from the host device. And then after finishing the device kernel execution, then we have to write data back to the host. But in this case, there are some inefficiency. For example, if you look at the OpenAC block 1 and block 2, actually, if you look at the green colored data, we have 3 copies. And there are some data transfer between host and GPU. But we don't have to do that. Because the second, the OpenAC block, also runs on the same device. In this case, we don't have to do unnecessary data transfer between host and the GPU. So what we did is that if we know that both producer blocks and consumer blocks are running on the same device, then we can reduce unnecessary memory transfer between host and the device. And this shows the example output of the sample workflow. And let's look at the performance comparison. What we did here is that we compare the performance of the OpenACC block-based workflow versus the original CPU implementation-based workflow. Then in this figure, red the block means that each OpenACC block, and green block means each reference CPU implementation. So if both blocks are labeled the same thing, that means that it does the same algorithm, but one is implemented as OpenACC, the other implemented as a reference CPU. And here, what we did is that we run the both OpenACC workflow and the reference CPU workflow on the same CPU. As I said before, OpenACC block provides 2 implementation, reference CPU implementation and the OpenACC implementation. So if we target the CPU, then even OpenACC blocks just use the original reference CPU implementation. So in this case, we have to see that both OpenACC block and the reference CPU block should run equally. But as you can see in the, for example, D2 case, D1, D2 case, our OpenACC blocks a little bit performs better than the reference CPU block, because when we implement the reference CPU version inside the OpenACC block, we applied very simple caching optimization that causes some performance difference. Let's look at the next case. In this case, what we did is that we offloaded the OpenAC block again on the CPU, but using the OpenMP as a backend programming model. That means that instead of using the reference CPU implementation, OpenAC block uses the OpenMP implementation of that block. So here we can see in some blocks, OpenACC blocks performed better than the reference CPU implementation. But in other blocks like the B and C, still reference CPU version performs better than the OpenACC block. Why? Because some of the original GNU regex implementation was vectorized using the bulk library. That means that here what we compare is that the version parallelized using the OpenMP multi-threading versus the version vectorized using the bulk library. So this shows that depending on the characteristic, sometimes it's better to use the vectorization and sometimes it's better to use the multi-threading. And next, what we did here is that we offloaded the OpenAC blocks of GPU, but without any optimization about the memory transfer. As you can see here, even though we offload the computation to the GPU, because of the extra overhead for the memory transfer between host and the device, in most cases, GPU performs worse than the CPU version because of the memory transfer overhead. But when we applied our memory transfer optimization, we could remove some unnecessary memory transfer. So in that case, in most cases, OpenAC block performed better than CPU block. But there is one exception, block A. In this case, still, the OpenAC performed worse than the reference CPU. It is because the original CPU implementation was vectorized using the bulk library. That means that still we compare against the vectorization on CPU versus the parallelization on GPU. So depending on the computation, it may still be better to run on the CPU using the vectorization. But in most other cases, if we can offload the computation to the GPU and optimize the unnecessary memory transfer, then we can beat the performance of the original reference CPU. And this is a little bit more complex, but I'll skip that. And so what we can learn from here is that once you create your blocks using the OpenACC and create a workflow using OpenACC blocks, then you can create one workflow that can run on the multiple different type of devices together. That means that part of your blocks run on the GPU and part of your block run on the CPU, another part of block run on the FPGA. That kind of true mixing of the heterogeneous device is possible if you use this framework.
Thank you, Seong. So just one thing I wanted to say about that diagram. We modified the GNU radio so that we could add some attributes to the blocks that actually let you say where to co-locate the blocks. Ideally, that would happen automatically somewhere along the way. So there'd be a phase where you could basically unify some of those blocks into a super block and then put them on an FPGA, for example. And so we're running a little short on time. I want to tell you about Iris. So Iris is our runtime system. And so we've looked around. There's a lot of runtime systems out there. We didn't find one that ran on all the platforms with all the different programming models we wanted to run for the reason Seong mentioned. You know, some nodes just don't support certain programming models well. And so in some cases, OpenCL is a great choice. On things like Xavier, OpenCL is not there, so you have to use CUDA and OpenMP. And so we created this to help both orchestrate the data movement and launch and manage tasks across a diverse set of system architectures. We have several different models here. We have a memory model that also will track with a directory where your data is in these different devices and inject data movement into the execution of the tasks if necessary. And it really looks like a DAG. So you know, everything in computer science at some point seems to get back to DAGs, but that seems to be working for us. We're not talking about millions of nodes. We're talking about dozens or maybe a few hundred nodes in our DAG. And then Seong talked about the programming models. Here's an example of what we're running across today. So with Iris, you can take it and run it on this node, for example, that has Xeon, Pascals, and Stratix 10 in it. You can run it on a Summit node using the requisite programming model on each chip, and then it runs on Radeon, Xavier, and Snapdragon. And we list out what software stack we use to do that. I don't have a demo. I didn't think I had time for it, but here's snapshots of it booting on all of those platforms, and you can get a feel for how it does that. Here it's, identifying that it has the CUDA platform available and loading the shared object for that and skipping things like HIP and OpenCL. So the task scheduling is interesting. Many of you already know about task scheduling. So the thing I want to mention here is that, we're actually getting to the fun part now. We've got this nice framework that has many mechanisms in it that let us schedule things, but we want to start exploring the device selection policies. Now, you could do a simple thing like have a hint, a pragma that says run all of these tasks on a GPU. But we could also look at things like the profile-based or the ontology-based, or one of the original ideas we looked at was using a performance model to give you a rough indication of where a task should be performed. And then once you have that, the task scheduler executes that on the ready queue every time. I've got a simple example here of a Saxby, and this is running on the Xavier using the GPUs and the ARM CPUs. Basically, what we want to do is run Saxby on the A times X on the GPU and the Y on the CPU. And so one of the things that I mentioned was that we do have dependencies. I'm running short, so I'm going to speed through this. There's a C++ interface to Iris, and there's a Python interface to Iris. The Python interface is right here. It's a lot easier to explain. You create, data regions with Iris. Then you can launch these tasks, and these tasks point to code. For example, right there's the CUDA code that gets launched when Iris submits this task and it's called up for execution. And you have to do the transfers and identification of how big the data is. There's also the OpenMP version. We have to execute a little pre and post execution code for these, but we think we can automate that with things like OpenARC. And then here's the execution, the memory management. So in this diagram, it doesn't really stand out very much, but basically what happens is when you identify these read-write dependencies on the different data regions, you're basically telling Iris, look, there's potential inconsistency there, and so you need to manage that. So it has a directory, and it knows to go in and move the data from one device to another based on the task being completed. All right, I'll jump forward. So the other thing was just that we're looking at efficiency. We're trying to get this execute where we can do almost 90,000 tasks per second on both the CPU and the GPU. It's online, so feel free to take a look at it and let us know what you think. And with that, I'd like to thank FOSDEM and SDR and DARPA and DOE for funding and inspiring our work. Thank you.
Thank you.